It's my great pleasure to welcome Ramesh Roskar, professor at MIT Media Lab, to talk about his view on AI and how can we deal with privacy and other issues with that.
Thank you, Rebecca. Well, driving up here, I noticed we are on Bunker Hill. Who here knows about the Bunker Hill massacre in Boston? So I think Thomas avoided death by PowerPoint. I'm going to try a massacre by PowerPoint. All right, so let's talk about making invisible visible. And I'm at the MIT Media Lab. Who knows this movie with Tom Cruise? Which one? Yeah, Minority Report. And there's a very cool shot where Tom is coming out of the elevator, and the cameras are zapping the irises to do, of course, targeted advertising by identifying it. But going forward, what if I told you that from where I'm sitting, I could potentially see the back of your retina at about 5 to 10 micrometer resolution, so we can look at the hemodynamic blood flow, right? And it's easier for me to see at the back of your eye than it is for me to see, say, 5 micrometers on your skin from here. And the reason for that is I can convert the lens in your eye to create a infinity corrected microscope, right? So this is kind of interesting that, of course, eyes are a window to future health, but now we can have an invisible way to look at the future of everyone, right? And of course, it should creep you out in terms of what we can do with this type of technologies. Nevertheless, you can imagine when we have consent, we could provide very non-invasive ways to look at invisible predictors, because the hemodynamic flow is excellent for detecting cardiovascular and other systemic conditions like diabetes and hypertension and so on. That was invisible predictors. What about invisible objects? Can you build a system that can see around corners beyond line of sight? So we started working on this about 10 or 11 years ago. And to do that, we use an extremely fast detection mechanism, fast enough to see light in motion. We call it trillion frame per second imaging. And it uses a very clever stroboscopic method to create light in motion. So here we're just going to shine a very tiny pulse, laser pulse into this Coke bottle. The light propagates through the bottle. Most of the photons travel in straight line, but some leak out on the table. They hit the cap of the bottle, light starts scattering. You see at the top of the bottle there's an air bubble, so light is bouncing around. And after several picoseconds, you see light concentrating back on the back of the bottle. There, right? And we can do this using a combination of sensors and electronics and processing and so on. And so with this type of photography, which we call femtophotography, because trying to achieve the resolution of 10 to the minus 12, 10 to the minus 15 seconds, we can start really building new types of imaging systems, right? So when we did this about 12 years ago in my lab at MIT, this was a little bit exotic, but since then, a lot of progress has been made. So, we can build systems to see through fog, for example. We can create systems that can see motion around the corners, maybe to look for survivors in hazardous conditions. Of course, we can build systems to avoid collision of fogs around the bend, and so on. And based on some of the work I have done, and my team has done at MIT, DARPA has launched a massive program called REVEAL, which is a $28-30 million program. And now we have many teams across the nation. Many of them are former students or faculty at top institutes, building systems that can see around corners, see through fog, and make invisible objects visible. So it's very exciting in that sense. And of course, you can use it for other applications as well. You can put this in an endoscope and create endoscopes that can see around your lungs in this case. And then you can start exploiting this time dimension in interesting ways. So the top left, this is from Barmak Heshmat. from our group, creating new types of optical jumble endoscopes that can just go in a disordered way and still create 3D images. On the top right, it's part of an NSF moonshot to get 5 micrometer resolution at 5 millimeter depth inside your body, which is kind of a cellular resolution. Bottom left, this is Guy Satat, now at Google X, working on measuring fluorescence lifetime and looking at the change in the lifetime based on the environment. And then Achyuta Kadambi, who's here, now a faculty at UCLA, working on things like how can we build a CAT scan in a rickshaw. Very portable, very reconfigurable setups. So kind of an exciting way to see how imaging and machine learning can make invisible objects visible. Again, Barmak Heshmat and Sanses worked on creating a device that can read a book without opening page by page. And I think when I was in school, my mom used to say, just put the book under your pillow, and somehow you'll become smarter. I guess we can indeed read through a book. And this one is using terahertz. And Matt Ronalds, another PhD from Media Lab, is here with his company TrueWave, and they're also showing very clever ways to use different spectrum, different electromagnetic spectrum to provide new types of imaging, new types of solutions. So that was about invisible objects and invisible markers. What about invisible data? And I'm going to mostly talk about this topic. And the data is invisible because we think there's a dichotomy between privacy of the users and the utility of what you can do. So if we did a thought experiment and somehow we can look at all the data that's out there, one could argue that majority of problems in health and transportation and energy consumption and even democracies could be solved overnight, right? But clearly, we don't have the consent, and we have to have the respect for individual privacy, so we don't know what everybody's doing and what everybody's thinking. But I think we've reached a point now in computing where this is actually a false dichotomy. We can achieve both at the same time. So let me share with you some really interesting developments in this space, which allows us to look at the data with extremely fine granularity, but still maintains privacy. And of course, a lot of this is work from my students and postdocs in camera culture groups. So please check our website for what we do also in the summer with a short course. All right. So I think there are 3 main reasons why there's a data friction and why data is invisible. First is that it's just a hassle to prepare the data so that we can collaborate with others, right? Data is siloed, it's not good quality, we need really good talent. The second reason is there is some actual barrier, such as privacy or regulations or just trade secrets. And even if you can overcome that, even if you can get the consent and use your lawyers and business people to handle the middle, the last one is why is it so useful? What's the incentive? Maybe other people will share with each other and they'll come up with the best solution and can just use the solution. Why do I need to share my data? And often this is being solved by saying you should make your data sets public, maybe you should contribute to science, and they're kind of appealing to people's desire to do social good to make this data available publicly. But I think that will go only so far. So let me briefly talk about 3 techniques in our group that we are developing to attack each of these areas. Automating machine learning, so-called split learning, and data markets. So let's do this, let's take this example. Imagine instead of a big data, we have a small data problem, which is, many hospitals, let's say, have x-rays of their patients, and we want to create a global solution that can detect pneumonia in x-rays, right? But let's say each of the hospitals, some have diabetics, some have smokers, some have children, some have elderly, or different ethnicity, different demographic. And we somehow want to bring all the data together, but clearly each of these hospitals, cannot share raw patient data. And from this local data, we want to create this global model. And I'm explaining this in the context of health data, but the same idea, same challenge is true in many other sectors. So the first thing would be, how do we automate this process? So our group started working in this space a few years ago, and the concept is called neural architecture search, which is you don't want to just fine-tune the parameters of your machine learning model, but you want the flexibility to select arbitrarily complex and arbitrarily different architectures, topologies of your network as well. And the basic idea here is you have a large teacher network, which uses reinforcement learning, as Vincent was talking about this morning. And the actual network that you care about creating, let's call it a student network. And the teacher network is going to spawn many student networks and to see how they proceed. In Vincent's case, he's using the reinforcement learning to do a particular task. In this case, the teacher is using the reinforcement learning to see how we can nudge each of the students to do better and better. And with this mechanism, the teacher observes, with just a little bit of data. Think of a student just being in the first grade and saying, you know what, after the first grade, you're doing really well, so I'm going to give you some more encouragement, so by the time you graduate, you'll be an amazing network. Or if you're not doing so well in the very first grade, then maybe I should give you a very different incentive, or maybe I should ask you to stop, right? The analogy with humans, of course, doesn't go very well, but it's okay to do that for student networks. And by doing this, the teacher, after many iterations, can find a winning network. And that winning student network, turns out, will have a very unique topology, very unique parameters, and whatever cost function that you have assigned to it. And what we have shown, very naively, that this simple mechanism of doing a neural architecture search can beat some of the best human crafted networks. Right? And this whole thing has, Google has another method to do neural architecture search, and this whole field has expanded now. Google even has a division for AutoML, self-search solutions. And we're going to see this trend percolate down to all interesting areas. So it's not just about creating new software, but creating new operating systems and even creating new chips for machine learning. And that's all based on automated machine learning. So we think with mechanisms like this, we won't need to deal with messy data. We don't need to worry about wrangling of data or janitorial work, as some people call it, or deploy very talented data scientists to deal with this data, because AutoML will take care of many of these issues. So let's talk about the second column, which is how to deal with privacy and trade secrets as you start sharing this data. So imagine these clients have very useful data, and the server wants to learn from all these clients, but of course doesn't have access to their raw data. So on the horizontal axis here, let's think about different ways to protect the data. And the most common way to do that in health settings especially is to anonymize, but that unfortunately has been shown again and again is not very secure. Some new strategies have emerged. You can obfuscate the data, add noise, so that if you're doing relatively simple operations like aggregation for averaging or histogram, then noise in individual entry will still not impact the aggregated results, right? The techniques such as differential privacy that are doing really well in this space. And of course, probably the best way to protect the data is to encrypt and not let the server know anything about your data, but only learn a bigger model. And there are techniques such as homomorphic encryption that are being deployed. Unfortunately, things like homomorphic encryptions are not good enough yet to utilize the data in a meaningful way. So on the vertical axis, when you think about compute utility, you can think about performing statistics like greater than, less than, histogram, and so on. Or you want to do an inference, for example, you want to do face detection or pneumonia detection, or actually training the model, which is, I'm going to collect a lot of data and create a completely new algorithm out of it. So as of today, differential privacy can be used for inference, and homomorphic encryption can be used for statistics, but none of them are good enough to actually train models on their own. So two techniques have emerged in the last 2 or 3 years. One is called Federated Learning, again by Google, which allows you to train, and I'll give you a 30-second tutorial on that. And another technique called Split Learning that my group has been working on, and that also allows you to train model without sharing raw data. And the basic idea, it seems like magic. How can you train a machine learning model without exchanging raw data? And the key kind of concept behind all these techniques is you want to share wisdom without sharing raw data. So if I have these hospitals with x-rays, I can take a lot of medical interns, this is an analogy, and I can say, go spend a month in each of these hospitals as a radiologist and become really good at figuring out how to detect pneumonia in smokers, how to detect pneumonia in diabetics, how to detect pneumonia in children, and so on. And you ask all those interns to come back to your office and say, hey, don't tell me which images you saw because those images are private and we don't have permission for you to share with me, but I just want your wisdom. And you create a room with all your interns, and when a new image comes in, a new X-ray image, one of those interns can tell you it has pneumonia or not, right? So that's kind of the basic idea of sharing wisdom without sharing data. Okay, sending interns and bringing them back. So this philosophy is actually very, very powerful. You don't have to think about encryption or obfuscation, and we can take this concept further. So again, let's say we have a machine learning model shown that in the red, green, blue colors, deep neural network, and you want to work with clients. You may have different scenarios. It's not just about an individual user. So if you have an individual user, and let's say you have a device, a phone, or some kind of an edge device, you probably care about things like user privacy. But if you're an organization, you care about regulations. I have all these data sets. I would like to be in this pooled collective intelligence, but I have limitations on what I can do with everybody else. And sometimes, you want to put data sets out there, especially if you want to work with, if you're a corporate entity and you want to work with startups or stimulate innovation in a particular space, you would like to put data sets out there, but then you're concerned that something will leak out of it, right? In case of health, often there'll be digital biobanks. They'll have data records of millions and millions of patients, and today they are taking the risk by just anonymizing it and releasing it, but as we know, that's not at all secure. So in all these scenarios, we need a mechanism to interface with the external world outside the organization, but still do it in a way that preserves privacy. And this is kind of a challenge that we must overcome if we have to accelerate machine learning in the fields that we care about. If we just care about, kind of consumer-facing applications in photos and videos and text, that's fine. But for most of the industrial applications, we need a very different way to move forward. So in federated learning, in 30 seconds, think of each of the client has X-ray images, trains a neural network model in the best way they can. Let's say each of the client has only 1,000 images. They do a reasonably they do a pretty poor job of training the model because very few users. And in simple words, that partially trained model from each of the clients goes to the server, and server simply takes an average of all those models. And if it doesn't so well, it sends a common average model back to all the clients, and they start all over again. Right? That's kind of a federated learning. Call it as kind of averaging the learning, averaging all the interns that you have sent out. And this actually works out pretty well when the number of clients is very, very large, in tens of thousands or even millions. Split learning, which is what we are working on at MIT, has a slightly different approach. So imagine you have a neural network, deep neural network model shown on the top left. We're going to take the early layers and we're going to split it. That's why we call it split learning. And the early layers will execute on the client. Think of it as a very thin client that's doing minimal computation. It converts the raw data into an intermediate smash data, and that smash data is what's sent to the server. And the rest of the training continues on the server. So early layer of the neural network execute on the client, and the later layers execute on the server. So the concept is very simple of splitting the work between the client and the server, And depending how quickly you're converging to your solution during training, the server can do a traditional backdrop and continue this process. So after doing 20 or 30 such runs and epochs, you have a somewhat, you reach an equilibrium and you have a good enough solution. So federated learning, split learning, very similar philosophies. In federated learnings, you're going to merge the learnings by taking average of all the models. Instead of merging the learning, here we're going to split the learning. Right? We're going to split the work between the client and the server. But this minor variation actually allows you to do some amazing things. In terms of compute and accuracy, you'll be 1,000 times, 1,000,000 times better than federated learning. In terms of bandwidth, also it could be 10 or even 100 times better than federated learning. And the convergence is more guaranteed than federated learning. And those of you think about kind of different types of clients. A client could be an edge device like an IoT device, or it could be a big organization like health data. And both these scenarios are not as compatible for federated learning because in IoT you have very low compute and communication abilities on the device, which means you can't really train a model that's being sent from the server. And also there's too little data per client for it to expect to start and updating a full-fledged neural network model. That's on the IoT and edge devices. If you have kind of enterprise data on the right side, then you have actually very few clients. Maybe only have 5, 10, of the order of tens of devices, tens of hospitals, sorry. And it doesn't make sense to do federated learning because the data is very non-homogeneous. And probably the most important difference between federated learning and split learning is that federated learning expects one organization to own the whole data ecosystem. Own the server, own the clients, and own the software as well. As opposed to split learning, where untrusted parties can collaborate with each other. I won't go over the slides, but it's a very detailed comparisons, and our slides are online at MIT as well. I'll skip over some of the challenges on achieving accuracy. And the third part of reducing data friction is how can we create data markets for machine learning. So there we have it. I think to make invisible data visible, I think we need effort in all three areas. How to automate the machine learning, how to create machine learning that works even if data is private or has trade secrets, and how do you create incentives through new forms of data market. Remember, the data market has to work even if data is private. So you cannot look at the data and you have to assign $1 value to that data. So I think when we think about pushing machine learning in many sectors, we have to make the invisible visible. And probably the biggest challenge we have today is to overcome the data. Thank you.
Thank you, Professor Oscar. Questions from the audience? Are you still thinking through what was he talking about?
Not in my sector.
Yeah. So,
Yes, go ahead.
So just a quick question on this. Is it still experimental, or are you trying to commercialize it or take it to market?
Sorry, which project?
This project that you were just referring to in terms of all the data and all this.
Yes, split learning and so on. So actually what we're doing at MIT right now is we are creating a horizontal standard that would spawn many industrial partners and many startups to build on top of it. So we invite you to join our standards activity for split learning. Think of it as a JPEG or encryption standard, because we all need to agree on what that standard is, so that untrusted parties can work with each other. In terms of image compression, you can compress with one device, decompress with another device, even if you don't know each other. And we think this notion of smashed data that will allow you to do machine learning, to taking raw data, converting into smashed data, would also require a similar standard. So we have a very nice activity at MIT.
Sure.
And
I'll reach out and talk further, because we were talking about data orchestration only a little bit back. So
Sure.
seeing that's what she.
Yeah. The website is splitlearning.github.io. Yes.
Quick question, maybe you covered it, but I missed it. One, two, yeah. When you look at your split learning versus the federated, You talked about the training mechanism, but I'm curious about what happened after you finish training and there's new images, let's say it's an X-ray scans coming in along.
Right.
What's the difference between the federated and the split when you are new, like new material, new data is coming in? Do you have to redo everything, or you keep somehow using the old models to continue and feed up the new data? What's the difference there?
Yeah, that's a great example. So if you have incremental updates or streaming data, for example, in federated learning you'll be in trouble because you have to update the models, send it back, ask all of them to update their models and synchronize in multiple ways. So even one extra update would have to create all this compute and communication activity. In case of split learning, you would just smash your data and send it to the server, and the server would train it. So the split learning, think of it more of an API model, where the clients are doing some initial work, but then servers doing most of the work for training. So it's a classic API model. The federated learning model is send the code where the data is, which sounds like a good idea to start with. Unfortunately, it doesn't fit a classic API model because you're sending code to the client. It works in some cases, such as if you want to train a model on Google phones or Apple phones, when you have tens of thousands, even millions of phones. But when you have untrusted parties, it becomes very difficult to orchestrate.